Hello students. So far we have seen several things in a recursive approach. So we'll cover some more stuffs on recursive approach in these slides. So there are some classifications of recursive approaches. So these are the some definitions how to classify some recursive approach. So these slides basically describe some of the way in which recursive functions are characterized. So some recursive functions, call itself, and some recursive functions are not called itself. So probably it calls it is called by other functions. So that depending on that, some recursive function is called direct recursive functions. Some recursive function is indirect recursive functions. So let's see some examples. So direct recursive functions and indirect recursive functions. So this one is direct recursive functions. You can see why it's direct recursive functions. So this is the full functions, and this is the base case of this recursive functions. If x less than 0, then return x. So that basically terminate the process, and that is a recursive portions of the recursive approach, this method, and it calls foo itself. You can see that foo is called from its definition. So that's why it's called direct recursive functions. So recursive approach calling itself, calling the method itself from its definition. That's why it's a direct recursive functions. What about the indirect recursive functions? Now you can see that these are the full functions. Full functions has some base case, and full functions called bar functions, and bar functions come to here, and bar functions call full functions again. So it's something like that. Full functions called bar functions called full functions called bar functions, and bar functions called full functions. It's some kind of a cycle. So this is also a recursive approach. You can see that why it's a recursive approach. This is a base case. You can understand that if x is less than 0, then you can terminate the process. Now when you call the bar functions, and these bar functions call full functions, and when you call full functions, that basically make the input smaller. So it was x, and x passing through the bar, and it's assigned to the y, and y then making y then the process making y smaller, and that smaller y is assigning to the x. So that means every time in this recursive call, x becoming smaller and smaller and smaller. So at the end, x will be a 0 or less than equal to 0. So that time it terminates the process. So this one is a direct because it's called itself from its definitions, and this call is indirect because it is called from other method. Both are the recursive functions, both have the recursive structures, both have base cases, both have non-recursive portions, both have recursive portions, both are making input smaller. And here you can see that x is becoming smaller every time, and both have some terminating process. So that's why it's a recursive approach, and this one is a direct and indirect recursive approach. Now, second definition saying that whether there are pending operation at each recursive call. So if there is a pending operation in recursive call, then it's called tail recursive. Otherwise, it's called non-tail recursive. So far, we have seen several recursive approaches. Those are the tail recursive because they have some pending operations, and pending operations. We'll see some examples. So you keep some arithmetic operations for later, and when you reach the base case, then you start to combine those in a solution, or so you do those pending operation to make a complete solutions. So in based on that, you can call that recursive approach is tail recursive or non-tail recursive. So let's see one example. Say for example, the recursive. This is the definition. A recursive function is said to be tail recursive if there are no pending operation to be performed and return from a recursive calls. Say for examples, this one this one is tail recursive because there is no any pending operations. So you can see that this is a recursive functions, this is a recursive functions, and it takes some n value, it takes some n value, and this is the base case. If n equal to 1, then return results. And this is a recursive portions, and these recursive portions that basically making the input smaller. You can see that it was n, then and second time it became n minus 1, and the computations happening at the same time, n multiplications of results. So you have some n, and that n multiplied with current results, and it gets some result, it gets some value, and that value is assigned into the results. So there will be no any pending operations when it reach the base case. So at it's basically doing operations at the same time when it calls the method itself. So far we have seen different things. They keep some, so let's go to that. Other things. Say if you go some, other operations, a non-tail recursive approach that we have done so far. Let's see one examples in our previous examples. Okay, so this one, in this one you can see that, so every time when it calls, this is the factorial functions, every time it calls but it doesn't do the operation, it skip all the operations for later. So these arithmetic operations are happening when it reach the base case. When it reach the base case, then it start doing operations. So if it reach the base case, then it do the multiplications, return, get some results, return to the caller, then multiply the result with 2, then get some results and return to the caller, and it's doing the same thing, I know, for each callers. So these are the pending operations. These are not happening at, during function is called. It basically happening when it reached the base case, then it started to calculate the computations. But here what we are saying that we are saying that these are, so these computations are happening during the function calls. So when there will be no pending operations, that time we call that this is a tail recursion method, tail recursive approach. When there will be a pending, that time we will call that non-tail recursive method. So this one is a non-tail recursive method. If there are pending operation to be performed on return from a recursive call, then we call the non-tail recursive method. So this is a factorial method. It takes n value. If n equal to 0, return 1. This is a base case, and this is a recursive portions. And you can see that n multiplications is happening, after calling n minus 1. But in previous, you seen that this is happening inside the function calls. This is happening inside the function call. However, here this multiplication is happening outside of the function call. Since it's happening outside of the function calls, so function call will be happen fast. Then it will get some results, and the result will be used to multiply the operations. So this is a non-tail recursive because these operations are pending, because it will be waiting for the results of the factorial n minus 1. But in that case, they will be not waiting. This operation will be not waiting for the function calls. They are happening at the same time of the function calls, get some results, and result will be assigned to these variables result. So these are the definitions of tail recursive and non-tail recursive. Now, so the third categories of the recursive function is that the shape of the calling pattern, where the pending operation are also recursive. So so sometimes recursive function is linear and sometimes is tree recursive. So that basically happen when recursive functions, in its recursive part, it call method recursively only one, only one recursive call are in the recursive portion, then it basically create a linear. For examples, if you go to the previous example, so this one, so you can see that these recursive functions, so this is a recursive part, this is a recursive part, you can see that these recursive portions happen, there is only one recursive call in the recursive part. So if you go other example, say this one, let's this one. So you can see that this is a recursive portion, recursive approach, and in this recursive approach, this is a recursive portions. These recursive portions have only one recursive call, only one recursive call. When you have only one recursive call, that basically create linear recursive call, a linear recursive call. If you have more than two recursive call in the recursion part, that basically create three recursive calls. So let's see one example when it will create three recursive calls. So this one is a linear recursive call because the recursive portion has one recursive calls, one recursive factorial. But if you see this one is not linear. Why this is not linear? Because you can see that this is the base case. If n equal to 0, return 0. If n equal to 1, return 1. Both are the base case. But if you see the recursive portions, so it basically fib n minus 1 plus fib n minus 2. So if it is a recursive calls, then it calls fib n minus 1 with the smaller inversions and plus fib n minus 2 more smaller inversions. So you can see that these recursive portions has more than one recursive calls in its part. So this is not a linear. This basically create three recursive. Why it's create three recursive? Let's see this. We'll explain this one. Why three recursive? Just try to understand that. In order to identify whether this one is a linear recursive or or tree recursive, you have to check the recursive portion of the method. If the recursive portion has one recursive call, then you can understand this is a linear recursive approach or linear recursive method. If it has more than one recursive call, then you can say that this is a non-linear or tree recursive approach. So these are the three different type of recursive approach. First one is direct recursive approach or non-direct recursive approach, and second one is tailed recursive approach or non-tailed recursive approach, and third one is whether it is a linear recursive approach or non-linear or tree recursive approach. We'll see some tree recursive approach examples also later. So we have discussed several times what is the difference between recursions and iterative. So both has some pros and cons, and both are doing the same things. The motivation is same things. Basically, if you need to apply same operation on several data, probably you can have a loop and you do the operations, and you can do the same thing in a different way, so in a recursive way. And recursive way, you have a loop and you do the you can apply same application, same method on several data. So when we compare pros and cons, probably iterative is more faster than a recursive call. Why recursive approach is slower than the iterative approach? Because recursive approach had some more operations. For example, they need to call function methods, then they need to create some stack, active frame in this run stack. Then they need to come back to the caller. They need to assign, some variables information to the callee parameters, and they need to return some return address to the caller. So those are basically extra, extra operations when you call functions again and again for doing some looping operations. So that's why when you think that recursive approach probably need more time to do operations, more space to do operations, then probably you will prefer iterative approach. So what is the benefit of having recursive approach? The benefit of recursive approach is simple to understand. It's easy to write. It has very small code, and it's look like mathematical operations. So people like to use recursive approach to make their code simpler and very basically easy to maintain. That's why people uh, you know like to use recursive approach. So in these examples, previous example, we have seen Fibonacci. So Fibonacci is a series, it's a mathematical problem. So we can solve this mathematical problem using recursive approach. We have seen that if n equal to 0, then return 0. If n equal to 1, then return 1. If n equal to other than 0 and 1, then it calls fib n minus 1 plus fib n minus 2. So you can see that there are two recursive call in the recursive portions, so that's why it's not linear, it's a non-linear or tree recursive. So if you write these definitions in a code, then you could have something like that. You have a method called Fibonacci, and Fibonacci takes some n value, and you have some base cases, two base cases. If n equal to 0, then return 0. If n equal to 1, return 1. These two are base cases, and this is the recursive portions, and the recursive portions called the Fibonacci n minus 1 plus Fibonacci n minus 2. So every time you call the Fibonacci with the smaller n, that basically moving towards to the base case. So if you have all the time n minus 1 and n minus 2 for each call, then probably you will reach at some time when n will be 0 or n will be 1. So in that case, you will reach the base case and you will terminate the process. Now since this is not a linear, this is a tree recursive, how does it look like? So it will look like something like that. So if you go to the tree, linear recursive tracing, you can see this one. You can see that every time we call, it basically create another call, another call, another call. So every call basically create one call, one call. That's a linear, one, 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 one. So that's why it's a linear. But when you have more than one recursive call in the recursive portions, it doesn't create linear. It's basically non-linear. So for examples, if you see that this is Fibonacci n minus 1, Fibonacci n minus 2, so when you have Fibonacci 5, so Fibonacci n minus 1 equal to Fibonacci 4, and Fibonacci n minus 2 equal to Fibonacci 3. So Fibonacci 4, then again Fibonacci n minus 1 equal to 3, and Fibonacci 4, Fibonacci n minus 2 equal to Fibonacci 2. Again Fibonacci 3 means Fibonacci n minus 1 equal to Fibonacci 2, and Fibonacci from Fibonacci 3, if you want Fibonacci n minus 2, then it is a Fibonacci 1. Similarly, from Fibonacci 3 to Fibonacci 2, because n minus 1, Fibonacci 3 to Fibonacci 1, because n minus 1. So you can see that in these calculations, you are doing same computations again and again. You see that Fibonacci 3, Fibonacci 3, Fibonacci 2, Fibonacci 2. So you are doing same operations again and again. This is kind of a limitation. So this is kind of a problem that you have to do the same operations again and again, and probably you can have some better solution also when you do some implementations, how to avoid some computations, duplicate computations. So when you reach some base cases, that time probably you return some results. When you return some results, then you can start calculating your exact solutions or complete solutions. So you can see that if you have multiple, more than one recursive calls in the recursive versions, that doesn't create linear structures, that basically create tree structures. So that means a function calls can create several functions calls, those several function calls, more several functions calls, is something like that. So now, so this is another way to write Fibonacci. So far you can see that This is one Fibonacci. So this is a a tree recursive approach. This is not linear, but you can convert them to a linear also. So this is the one solution how you can convert a non-linear or tree recursive approach to a linear approach. This is kind of a solutions. You have some variables current and previous. If n equal to 1, then need to return current. This is a basic base case. And in the recursive case you have fivo car plus previous car current and n minus 1. So you have n minus 1. This is your smaller input that will moving towards the base case, and these are the calculations that basically avoiding tree recursive approach. So in that case, if you don't have tree recursive approach, you don't need to do some duplicate operations. In tree recursive approach, we have seen that you have to do some uh, duplicate operations. So here this is a linear versions of the Fibonacci recursive approach. So you can do in that way. So now let's talk about the two basic searching algorithm in a recursive way. So first one is linear array search. So linear search algorithm. So that basically what you're saying that, for examples, you have an array and you try to find out some data from that array. So how do you find? So let's draw some figures and try to understand. So let's have some array over here. So we create an array over here. Say for example, so you have an array, and this is a some some data. So you have an array. Make it smaller. 5. Okay. So 5. You can see 5, right? I'll make it a little bit bigger. Say 8. Okay. So then you have some more cells. We'll update this data. Now update it. So for example, so you have 9 over here, uh, 5 over here, 1 over here, then you have 2 over here, then you have 6 over here, then you have, say for example, 10 over here. So now if you want to look for 6, this is your array and you are searching 6. So probably you have some recursive approach, or you have some for loop. What you need to do, you will check this one whether this one is a 6 or not. No, this one is not 6. Then you will check this one is a 6 or not. No, this one is not 6. You check this one, you will check this one, then finally you will reach at positions where 6 will there. So you compare 6 is there, so you found that there is a 6. So now if you want to find 11, so you'll check this one, this one, this one, this one, this one, this one, and you found that there is no any 11. So this kind of search basically called linear search. You check one by one. So you check one by one. This is one kind of searching approach. The how do you find how to search something from an array. So you check one by one. So you can search using an iterative way. You have some for loop. Inside for loop you check each element of the array, and if you find the results, then you return the results. And you can do the same thing in a recursive way also. So how do you do in a recursive way? So for examples, so you go to the slide, this one. So when you design your recursive approach, you have to maintain the several things. You have to have base case, you have to have recursive portions, you have to make your input smaller, and that should be towards to the base case. You have to follow those things. So now you have to design your base case. If array is empty, then the result is -1. That means you didn't find your target value. So this is your negative base case, that you didn't find your result. And this is also a base case, and it's terminate the process. Now your positive base case, if the first element matches the target, the result is found. That means this is your positive base case. So if you found the results, if the first element matches the target results, then you found the result. You found your target value. That means you can terminate the process, and this is your base case. And if these are not true, if these are not satisfied, then you call the linear search algorithms, linear search algorithm with the smaller portions of n by excluding the first element of you know array, by excluding the first element of array. So this is a recursive opera, how you can find it. For example, say let's go to the file again. So if you try to write some code to find to do some linear search using array. So you have I equal to 0, then I less than n, and I plus plus, and you check that if, say for example, so this is array A, if ai equal to your target value, then you find results. Okay, this is your uh, uh, this is your your uh, linear search using for loop. Now if you don't find these things, then probably you return. So for example, so you return target. Okay, so if you don't find, then probably you return -1. So this is your for loop style to do the linear search. Now if you have linear search process in a recursive way, so probably you will have linear search method, and you take some array or n value, right? So in that case, so you have to do, so you have some array, say for example some array, and now you have some conditions. Base case, if array length equal to 0, then probably you didn't find your target value, you return -1. This is your negative base case. And then you have positive base case. So else, say for example, else array, your first characters of array equal to target, then you return, okay, return array 0, array 0. This is your positive base case. Now you have to do your recursive case also. How do you write your recursive case? You call the linear search method. Say for examples, you call linear sorry, spelling is L-E-N-E-A-R, linear. Then you have here, you call linear search method with the smaller portion of input, means you exclude the first character. So you pass array from 1 to n. So that means you remove the first characters, first element 0. So index 0 is excluded over here. So that means we know that array basically has 0 to say n-1. Okay, 0 to n-1. So now this is your basically array size. Now you can do same thing. So you just exclude it fast characters. So we have the similar kind of problem. So let's see similar kind of problem, say in a strings. Here you can see that every time when we are counting the string, every time we give some input by excluding the fast characters, right? So in the definition also we have seen that exclude the fast characters. So similarly we are doing the same thing in linear search. In linear search, we just exclude the fast characters of the array. So if you exclude the fast character, then we are making our input smaller and smaller, and at some point array length will be 0, or we will find the target value at 0 index. So this is the linear search happening, using recursive way. So these are the things that we are trying to find out. So linear search basically find one by one, check one by one until it finds the target value. Here you can see that in a recursive approach also, it's checking fast character. If it is not satisfied, then it call the linear search with these portions of 5 to 10. Then if 5 is not satisfied, then it call the linear search with these portions 1 to 10. Then it not satisfied, then it's called 2 to 10. Then it's not satisfied, then it calls 6 to 10. When it calls 6 to 10, the fast character is 6, and it's basically target value. Which one was our target? 6 was our target. So this is the way how you can use a recursive approach for linear search. Now we'll see some other searching things. Where is that? Okay. So this one is a recursive approach for linear search. Now we'll see the recursive approach for binary search. What is binary search? Binary search is something that you can have efficient searching algorithm for searching something. So you can see that a linear search, you have to check each and every element to find some data. If your data is not exists, then probably you need to check whole array. So if you consider that array has millions of data, that means you have to check millions of data, and this is not efficient. The complexity of the linear search is big O N complexity. But if you want to have some better complexity, probably binary search algorithm is better options. The only restrictions of binary search algorithm is that your data should be sorted. So it cannot be applied to an unsorted array. So here this is an unsorted array. Now if you make it sorted, so for example you have 1, then 2, then 5, then 6, 9. Now you can see that this one is just sorted. 1, 2, 5, 6, 9, 10. Now if your array is sorted, then probably you can apply binary search algorithm. So how binary search algorithm happen? So what you need to do, you probably take the middle value first. If the middle value matches with your target value, then you found the results. If it doesn't matches with the target value, if your target value is lower than the middle value, then you go to the left side, and if your target value is greater than your middle value, then you go to the right side. For examples, you are looking for 6. Since if you are looking for 6, if you take this one is your middle value, then you know that you check that, okay, 5 is not equal to 6, so this is not our target value. So but 6 is greater than, our target value is greater than this middle value. So 6 should be right side of this middle value, it never be left side of the middle value. So you go to these portions. So when you go to these portions, so you have only these portions. Okay, you go to these portions. Now your array is these portions. Okay, so let's copy this one. Okay, copy this one. Now you have these portions. Okay. Okay. Now take the middle value. Say for example, middle value of this portion. So you have middle value this one, and middle value is not your target value, but your target value is lower than this middle value. So your target value should be left side of this middle value. So you only take these portions. When you only take these portions, so only take these portions. Let's copy this one there. Okay. So you have only these portions because you know that your target value is lower than middle value. So your your target value should be there. Then you take your middle value. So this one should be the middle value. There is only one element. So you check with the target value with the this value, and you found that yes, this one is a 6, and you find the result. Now check how many comparison you have done. You compare this one, okay, one comparison. Sorry, one comparison, then you compare this one, two comparison, then you compare this one, three comparison. So within a three comparison you found your target value. So this is the benefit of binary search, that if your array is sorted, then probably you don't need to search a lot of things to find any data. But if you have linear search, for example, so you have linear search, then probably in order to find 10 you have to check the 1 2 3 4 5 6. In order to find 6 you have to check 1 2 3 4, 4 comparison, but here is a 3 comparison. And if you want to find 10, probably you need only 2 or 3 comparison for binary search. So linear search taking more comparison, it needs more operation to do that. That's why it's inefficient. It takes big O and square, big O and complexity. However, binary search is not taking big O and complexity because you don't need to check all the element to find something. You take the middle value. If the middle value is the target value, then you found the results. If middle value is not your target value, then go to the left side or right side based on your result, based on your target value. And in order to do, if you do that, you probably skip so many comparisons, so many operations. Basically the complexity for binary search algorithm is log n complexity. So log n complexity is something that is very efficient than big O and complexity. So we described this log n complexity in complexity lecture. Now go to the slides. So how we can define a recursive approach for binary search algorithm. So binary search algorithm, so you have to write some some base cases. If array is empty, the result is -1. This is negative base case, similar to the linear search. If middle element matches the target, then result is found. That we have seen that this is your positive base case. If middle element is your target value, then you found. And if the target is less than your middle element, then recursively call this searching algorithm with the left portion of the array, and before the middle element, and return the results. Okay, so if the less than, so you call the searching algorithm recursively with the left portion of the array. So this is a smaller version of your input. That means you are moving to your base case. If the target value is greater than your middle value, then you call the searching algorithm with the right portions of the array. And this is also a smaller version of your input symbol, input data. So in both cases, both are moving towards the base case, and that's why this is the way how we can call recursive portions, a recursive approach. So if you write code in a binary search algorithms, say for example, if you convert these linear search binary search, probably you have an array and you have some middle value and you have some target. Okay, so if array length is 0, then return 1, you didn't find. And if array mid value is target value, return mid. So this is your positive base case. Now in your recursive case, you have binary search, and the array should be based on else if, say else, sorry, this one's if. So else if uh, array mid less than, or you can write your target is less than array mid, then you call binary search. So since target is less than array mid, that means, you know, uh, that should be the left side. So you call, say for example, 0 to mid minus 1. Okay, so this is the left portion of the array, and you call your target value is now, say you calculate some target value by using some, length, you know uh, new array. So you can calculate mid value over here. Say for examples, you can calculate over here mid value. You don't need to do here. So before going process, you calculate mid equal to array dot length divided 2, and this is how you can calculate mid value over here, and this is your target. Okay, now the other recursive portion is if else, then you call binary search with the right portion of the array. The right portion of the array. Right portion should be mid plus 1, mid plus 1, your n value, or n minus 1. So this is your late portion of the array, this is your right portion of the array, and this whole thing is a recursive portion. These are the base cases. These are the two base cases. So this is how you can write, recursive approach for binary search. You can write a recursive approach for linear search algorithm. You should try some exercise using recursive way, so you will understand. And this one is already we have discussed that a recursive data structure is one that has another version of itself as a component, and we can define a linked list as a recursive data structure. We have started with the recursive approach by giving some example of list. That list has recursive definition in itself. So a list has definition of a list itself. So similarly, linked list has definition of the linked list itself. That's why these are called recursive data structure, that you have several data, and you can apply similar functions on those data structures. Thank you very much. We'll see you for next slide.